this week's lecture, we'll talk about data representation and probability. In the previous week's lecture, we did go through data representation briefly through the R tutorial when we were looking at descriptive statistics. However, we'll go into more depth with these charts, and we're also going to look at basic probability. Data representation is a way to visualize the variables and data within a data set. The data set on its own, so the actual data frame in R or the table that you are looking at in Excel, etc., is not really useful on its own because humans don't really have the capacity to look at that amount of information and make sense of it without using some sort of data representation in the form of a chart or summary table. There are different ways to represent different types of data, and with categorical data, we can summarize data within a frequency distribution table, or we can use other categorical methods such as bar charts, pie charts, a word cloud, etc. So this is an example of a frequency distribution chart where I took the top 5 most popular Airbnb locations by city, and I summarized the number of Airbnbs within each city. And the relative frequency is simply the frequency or number of Airbnbs per city divided by the sum of all Airbnb locations for all 5 locations. Then the percent is simply the relative frequency in percent form. We will also go through the other types of categorical data representation in the R tutorial, but it is something we also went through in last week's tutorial. In terms of numerical data, we have different types of representations such as frequency distributions, cumulative distributions, or stem and leaf displays. The first is a histogram where you're listing in this example, the cities where Airbnbs are located along the x-axis or the bottom axis. And on the y-axis, you have the number of Airbnbs in each city. So the bar represents the number of Airbnbs in that designated city. For a cumulative distribution, we can create an ogive chart, which is shown here. In this example, we have the tweets by Donald Trump. So this is the same data set we were looking at the other week. And along the bottom, we have a time series from February 2020 to January 2021 when he was banned from Twitter. The red line also indicates the presidential election. And you can see the number of tweets per month increases over time steadily, which means that each month he's tweeting about the same number of times. But because this is a cumulative distribution, it looks like it's increasing over time, but it's actually just that he's steadily tweeting every day, or every month rather. This is an example of a stem and leaf plot where we, in this example, show the prices of Airbnbs in Los Angeles within the $200 to $250 range. So along the left-hand side, you have the first 2 numbers within each price. So the first one is 20. So 20 represents the first 2 numeric values in $200. And to the right of the pipe or the line, you have all of the single digits that are appended to the 20. So you'd have 200 shown multiple times, probably about like 20 times in this stem and leaf plot. then you have $201, $202, $203, and 2 Airbnbs that are $204. So you can see the distribution or the number of Airbnbs that have each individual price tag. And you can see also the lowest value in this range and the highest value in this range. You can modify the code of a stem and leaf plot, as we'll show you in the tutorial, and it will change the way the stem and leaf plot is actually displayed. You can also gather the distribution or most popular Airbnb prices within this range. This is a scatter plot with a trend line. The trend line itself is a regression model that describes the data set. However, we won't talk about it now, but in the future of this course, we will discuss what that trend line is actually showing. The scatter plot itself is merely the X and Y axes with the points plotted onto the graph. So in this case, we have a Goodreads data set where on the bottom or x-axis, we have the number of text-based reviews, and on the left, we're showing the average rating a book received. And lastly, we have this choropleth map, which is showing the cost of living in 2020. And this is a way to geo-visualize a data set. In this case, it's the cost of living per country or by country. And you can see the cost of living legend in the bottom right, and then the color-coded countries to indicate the cost of living. So this is the first concept that will really start getting into statistics and what they're really used for. So the first concept you have to understand is probability, because almost every statistical model is based on probability. So the term statistically significant is based on probability. Inferential statistics sounds like a very intimidating word, and it might sound confusing, but if you break it down into its components, it's not really that intimidating. So the word infer just means that you're concluding from some sort of evidence or some sort of reasoning that whatever the outcome is true. Building on that, you would then define inferential statistics as just drawing conclusions about a population, which is people or some sort of inanimate object like a grouping of trees, by analyzing the variables, patterns, or processes at play. So inferential statistics isn't actually that kind of complicated. You're just looking at data and drawing a conclusion from it. The purpose of inferential statistics is simply to understand our world better. If we understand our world better, then we can make our lives better as a result. So if, say, you understand how people prefer to commute to and from work, you can then create transportation infrastructure that makes commuting easier. And we can also take information and project or estimate into the future and predict how people will interact with that transportation infrastructure to make our future lives better as well. And lastly, as I kind of mentioned at the beginning of this slide, is that inferential statistics is based very heavily on probability and probability distributions. So that's why we're going to go over the basics of what probability is, and then we'll talk about probability distributions. So I thought a great example that we could go through for probability is the board game called Settlers of Catan. Many of you are probably already very familiar with this game, but for those of you who are not, or you've never played this game, it's okay, I'll explain the basics so you can understand the example. So essentially, the objective of the game is to collect resources in order to build things. And once you build things, you get points. So you can build roads, settlements, or cities. And the basic mechanic of the game is that you have settlements on these resources, and you roll 2 6-sided dice, and based on the number that is rolled, it coincides with the resources that you are settled on, and you get those resources. So the basic strategy of the game, obviously there are many strategies of this game, but the basic one is to place your settlements on resources with a number that will come up frequently with the dice rolls, so that when you're rolling the dice, there are certain values that will come up more often than other ones, and you'll get more resources as a result. And on the right of the slide, you can see the board that is typically used, and it can have different configurations of tiles, which gives the kind of more randomness of the game. But you will place your settlements on the nodes in between different resources. So you can see here in this example, I have selected 2 nodes as a settlement, as starting settlements. And you can see on the settlement to the left, I have wood, which is the trees, and it's on an 8. The ore, which is on the mountain tile, it has a 3. And I have clay, that is that orange kind of brick tile, with a 5. And then on the right side, I have another settlement, and it has wheat, which is that basically the farm field with the value 4. I have then 2 tiles that represent sheep, which are the fields, the green fields. So 5 and 11 represent sheep. So once you've actually put your settlements down and you have now tiles where you can get resources, you can start playing the game. The basic concept of probability for rolling a dice, so a 1d6 or 1 6-sided dice, is that the probability of rolling a 1, a 2, a 3, 4, 5, or 6 is 1 in 6. So there's only one value per side, and there are 6 possible sides for it to roll on. So 1 divided by 6 is 16.67%. So the probability of rolling any one number on a 6-sided dice is 16.67%. Now, it gets slightly more complicated when you're rolling 2 or more dice at a time. So if you're rolling 2d6, so 2 6-sided dice, you have a probability of rolling a 2, a 3, a 4, 5, all the way up to 12. And because there's 2 6-sided dice, and both of them have the numbers 1 through 6, your probability of rolling certain numbers are higher than rolling other numbers. So the probability calculation becomes the probability of die A multiplied by the probability of die B times the number of opportunities you have of rolling that value. So if we look at this very simple example, the probability of rolling a 2 with 2 6-sided dice, or the probability of rolling snake eyes, is 1 over 6 times 1 over 6 times 1. So you have 1 out of 6 chance of rolling a 1 on die A, and you have a 1 out of 6 chance of rolling a 1 on die B. And then you multiply that by the number of opportunities you have of rolling a 2. There's only one possible combination of die A and die B to roll a 2, which is a 1 on die A and a 1 on die B. So there's only one opportunity, so you multiply it by 1. So 1 over 6 times 1 over 6 is 1 over 36 times 1 opportunity is 2.8%. So the chance of you rolling a 2 or snake eyes on a 2d6 is only 2.8%. So now we'll kind of dive into this example of Catan, or the Settlers of Catan. So recall that settlement 1 has wood if you roll an 8, clay if you roll a 5, and ore if you roll a 3. Our second settlement has wheat if you roll a 4, and sheep if you roll an 11 or a 5. Let's look at the probability of gathering wood as our first example. So to gather wood, we need a dice roll of 8. So in the chart on the slide, I have every combination of dice A and dice B that create a dice roll of 8. So you could roll on dice A a 2 and a 6 on dice B. You could roll a 3 and a 5, a 4 and a 4. And then, very importantly, you could roll a 5 and a 3. And you might be thinking, well, a 3 and a 5 is the same as a 5 and a 3. But that's not true, because dice A is independent of dice B. So every combination there is listed, and each probability is listed separately. So you can do the chance of rolling an 8 with a 2 and a 6 is 1 over 6 times 1 over 6. And because there are 5 different combinations of dice A and B that create a dice roll of 8, we're going to multiply the 1 over 6 times 1 over 6 times 5. So 1 over 36 times 5 is 13.89%. So every time someone rolls the 2d6 or 2 6-sided die, the chance that you're going to gather the resource of wood based on your settlements here is 13.89%. Now let's look at the probability of gathering clay. So you need a dice roll of 5 to gather clay, and there are 4 different combinations of dice A and B that create a value of 5. So in this case, we'll do 1 over 6 times 1 over 6 times 4 opportunities, which is equal to 11.11%. Next, we'll look at the probability of gathering ore. So to gather ore, you need a dice roll of 3. There are only 2 combinations of the dice that create a value of 3, which is 1 and 2, or 2 and 1. So 1 over 6 times 1 over 6 times 2 opportunities is equal to 5.56%. Now, to gather wheat, we need a dice roll of 4. There are 3 combinations of the dice that will create the value of 4. So 1 and 3, 2 and 2, 3 and 1. So 1 over 6 times 1 over 6 times 3 opportunities is 8.33%. Now the last example is for sheep. And in this case, you have 2 different values that will result in you collecting sheep. So you can get an 11 or you can get a 5. So in this case, your 11 can be created with either a 5 and a 6 or a 6 and a 5. And then the combinations to create a 5 are 1 and a 4, 2 and a 3, 3 and a 2, or 4 and a 1. So that's 4 additional opportunities. So in this case, you'll do 1 over 6 times 1 over 6, and then multiply that by 2 plus 4, because you have 2 opportunities to create an 11, and you have 4 additional opportunities to create a 5. So 1 over 6 times 1 over 6 times 6 is equal to 16.67%. Now, what we can do is calculate the probability of gathering any resource per roll. So we can gather a resource based on a roll of a 3, a 4, a 5, an 8, or an 11. So if you just look at the previous slides, you can see all the combinations and the number of opportunities to roll each of those values. So in this case, just like in the last slide, where you have 2 chances to get a sheep, we're just looking at all of the different combinations. So we'll do the probability of rolling any of those numbers or gathering any resource is equal to 1 over 6 times 1 over 6 times 2 plus 3 plus 4 plus 5 plus 2. So if you add up those numbers, that's 16. So 1 over 36 times 16 is 44.44%. So you have a pretty good chance of gathering at least one resource on every roll of the dice. So now that you understand the basics of probability, we can now learn how probability is influential to inferential statistics. So a probability distribution is essentially a function that gives the theoretical probability of observing a specific outcome within a certain range of values. And I feel like the picture of a probability distribution probably makes more sense than the definition. So this is what is known as a normal distribution. A normal distribution is symmetrical from left to right, and in a perfect normal distribution, the mean, median, and mode will all be equal to the same value. And this is also what's known as a bell-shaped curve, where the line that is drawn to create the shape of the normal distribution will never actually touch the x-axis infinitely. And the area under the curve can be calculated, which then tells you or represents the probability of that event occurring. So based on this normal distribution, you can take any place on the x-axis and it'll tell you the probability of exceeding the value either in the right or left direction. And an example, the simplest example of this would be if you're looking at the direct center of the normal distribution, you would just have a 50% chance of either exceeding this threshold to the right or exceeding it to the left. So either positively or negatively. So in order to calculate probability, we need to take the normal distribution of values. So if you have a data set and you're looking at a variable, the actual observed values will be placed on this normal distribution. And we need to convert those values, those actual raw observed values, into standardized values so that we can actually measure the probability. And in most cases, the units are in standard deviations, and these are also called z-scores in most situations. And the standard deviations are representative of a specific value of the area under the curve. So one positive standard deviation is 34.13% of the area under the curve between the 0 and the positive 1 standard deviation. The area under the curve between -1 and positive 1 is just twice that of the positive 1. So 34.13% times 2 is 68.26%. So that's the area under the curve between -1 and positive 1. From positive 1 to positive 2 is 13.59. So the area under the curve between 0 and positive 2 is 47.72%. And again, for positive 3, you're just adding up all of those percentages of the area under the curve. And if you want to do -2 to positive 2, you would just add up those 34.13% plus 13.59% and then multiply that by 2. And based on these standard deviations, we can then calculate the probability of exceeding a specific value. So once you've calculated a z-score, which I'll show you how to do both in the slides as well as our tutorial, you can look on this table, which is known as a standard normal table or a z-score table. And you're looking for your z-score first on the y-axis of the table and then on the x-axis of the table. And this will make more sense when we look at it. In reality, you'll probably never use a z-score table outside of a stats course. And you're probably thinking, well, why do I need to know how to do it? It's really important to understand how this actually works in order to understand the statistical outputs that you're getting in R and other stats programs. So the first example that we'll look at here is looking at resting heart rate for healthy individuals in a normal distribution. And I just want to stress that this is not real data. So if you're not within this mean or the first standard deviation, don't panic. I'm not a medical doctor. Talk to your doctor if you're concerned, I guess. But anyways, the example is 70 beats per minute. That's the mean. And the standard deviation is 12 beats per minute. So we want to find out what the probability of an individual's resting heart rate will exceed 85 beats per minute. So what are the chances that a person's resting heart rate will be 86 or higher beats per minute? So the first thing we can do is calculate the z-score. So we're specifically looking at the z-score of a resting heart rate equaling 85. So what we do is take the resting heart rate and subtract it from the mean resting heart rate. And we take that value and we divide it by the standard deviation. So in this case, 85 is our resting heart rate. That's the threshold that we're looking at. We want to subtract the mean, which is 70. And then we do 85 minus 70 is 15. And then we divide that by 12. And that gives us a z-score of 1.25 standard deviations. So what we do then is we'll look on this table. We'll first look for 1.2 on the x-axis, and this is shown in red. And then we have on the x-axis, I meant to say on the y-axis, we look for 1.2. And then on the x-axis along the top, we'll look for the 0.05 because we're looking for 1.25. So 1.2, 5, and where it intersects there is our z-score. So our z-score is 0.3944. And this z-score on its own represents that in our distribution of resting heart rates, 39.44% of people will have a resting heart rate between 70, which is our mean, and 85. So now we can calculate the probability a person's resting heart rate will exceed 85. So to calculate that, we can do 1 minus, and then in brackets, 0.5, because 0.5 represents the area left of the mean under the curve. Since the area under the distribution is always 1, because it's 100% of the area. So 0.5 represents to the left of the mean, and we're adding it to 0.3944, which is the percent we got, or the z-score we got from the previous calculation. So 0.5 plus 0.3944 is 0.8944, and then 1 minus that value gives us 0.1056. So the 0.1056 represents the area under the curve exceeding 85 beats per minute. So there's a 10.56% chance that an individual's resting heart rate will actually exceed 85 beats per minute based on our mean and standard deviation of the population. And based on this concept, we can actually map the probability of exceeding a certain threshold by some sort of aerial unit. So this is the example from the R tutorial where I calculated the probability of a country exceeding 2,000 millimeters of rainfall in a year, and I mapped it by the country. So you can see which countries have a much higher percent of exceeding this threshold, mostly countries in kind of rainforest areas. So I hope that gave you a good understanding of how both we can visualize data as well as the fundamentals of probability and how to calculate probability for inferential statistics. The next thing we'll do is go through these concepts in R, and I'll show you how to do a lot of these things with R code. All right, so now we will go through the lecture content in R, and I'll show you how to do everything. So as we're talking about in the last lecture, you open your project here, and it'll open the folder down here in the bottom right. And we're just going to click on the RMD file right here. It's indicated by this little icon with the page in the RMD. It's very hard to see with the red circle. Click on that and it'll load up the script. Again, if you haven't installed these packages, say for instance we need these two packages, you've probably already installed Tidyverse. You can select these two lines of code, go Control-Shift-C or code comment/uncomment lines, and then you can run this code with the play button. I'm not going to do it because I already have these packages installed. However, you will of course need to load your libraries as normal. So go ahead and click the play button to load these libraries to tell R to look for these functions that you use in these packages. We're going to use two different data sets for this tutorial. First one being the Trump insult tweets data set that we used in a prior our tutorial. And then we're going to use the Airbnbs of the United States like we did in the last tutorial. So go ahead and run this code. This imports the tweets CSV, and we're going to just call it tweets. And then AB is Airbnbs in 2020 in the US. So the first thing we need to do is clean the data set. So this will create a new column called char_count, set it equal to the lapply function. So what this function does is it tells R to look through every row of the data set and complete this function. So it's going to look in every row of the tweet column. So tweets $tweet. So this is our variable. And it's going to use the string length function. So it's going to count the number of characters in each tweet per row, and it's going to calculate the number of characters in each tweet in each row using the lapply. So let's run that. Control Enter. And then once you hit Control Enter to run a line of code, the cursor automatically goes to the next line. So you can then hit Control Enter again to run the next line of code. This is just taking this information, and it's just this line of code is outputting a value, the length of the tweet in characters. And this line of code is just making sure that these numeric values are actually numbers and not text. So that's what that does. This line of code is just overwriting the tweets. So we're going to create a new data frame called tweets, but since there's already a tweets data frame, it's just going to overwrite it. We're going to input the current tweets data frame, pipe it into the filter function, and we're going to remove using the exclamation mark, remove any row where the character count, so the variable we just created, anytime the character count of a tweet is greater than 280, we're going to eliminate that from the data set. And this is just to make sure that none of the tweets are in error, since the Twitter's hard limit of characters for a tweet is 280. So I'm just going to go ahead and run all of that code all at once. Now moving on, we are first going to look at categorical data, and specifically the frequency distribution table. So we're going to create one using the code, and it's going to output as the one you saw in the slides. So we're going to create a new data frame called AB_freq, so frequency. We're going to input the AB data frame and pipe it into the select function. So select is used to select specific columns or variables in your data frame. All we want to do is select the city column. And if we just run this on its own, so you can just actually select part of a code block and run it so you can see line by line what's going on. So let's create the AB_freq data frame, and we'll look at it now. You can see if we look at the AB data frame, there's all of this data here. And if we look at the AB_freq data frame we just created, we can see that we only selected the city column. And we will pipe this data frame that we just created into the next function called group by, and we're going to group by the city. So if we scroll way down here, you can see there's multiple different cities. So this is Clark County. The first one at the top is Asheville. And so we're going to group by the city name. We're going to then pipe that information into the next function called summarize. Summarize is going to take the groupings that you just created, and it's going to count the number of rows per city. So it's going to create in this case, a column or variable called freq, so FREQ, and we're going to set it equal to the n function. So n, again, counts the number of rows per grouping, and in this case, we're grouping by city. So once we do that, I'll actually just run this code so you can see what's happening. So AB freq, so it's now grouped by the city, and it counted the number of rows per city. So the number of rows per city is representing the number of Airbnbs per city. Now what we want to do is arrange this data or sort the data by the number of Airbnbs in the city. Yes, we can just sort it by clicking these arrows, and it'll sort it either largest to smallest or smallest to largest. But we want to do that with code. So we're going to pipe this data frame into the arrange function, and we're going to say we want to arrange the data frame by the frequency column, and we want it to be descending. So we want it to be largest to smallest. So let's go ahead and run that those lines of code. And you can see here now it is New York City is at the top because it has the most Airbnbs in the city. And all the way at the bottom is Pacific Grove, where it only has 179 Airbnbs per that city. Now what we want to do is just select the top 5 cities with the most Airbnbs so we can create a graph using it, or create a table. So let's do that, and you can see what happens. So now you can see just the top 5 cities are now selected. And then what we want to do to actually create the frequency distribution table. So we already have the frequency or the count. Now we want to create 2 more variables. So we want one that is relative frequency. So it's a decimal percent. And a second column or a third column called percent, which is just the actual percent value. And you can see the formulas for each of these right there. And we will go ahead and run this. And you can see now we have the city, we have the frequency, the relative frequency, and the percent. So it's easy as that. And now if you wanted to output the table into the actual RMD file, you can just simply relist or just take that data frame and just paste it there on its own line of code. And when we run that line of code, it'll just output the table directly into the RMD file. So you can see here with the city, the frequency, relative frequency, and percent, and it's ranged from the largest number of Airbnbs per city to the lowest, but it's only the top 5 cities in this case. And you can see here we have our sentence to kind of answer the question of what the city is with the most Airbnbs. And this line of code here, so again, these 2 asterisks on each side just bolds this line of code here. So the back quote R and then space allows you to create inline code, and then at the end of your code you're going to have another back quote. And this is the code that you will use to select the city with the most Airbnbs, or the highest or max value of frequency. So what you want to do is you'll list the data frame. So in this case, AB_freak, $. Oh, I'm just going to undo that. $, to select the city variable or city column. So we want to select one of these cities in here. That's what this is saying. The square bracket then allows you to, I'm actually missing, I think, a square bracket at the end there. So that's important. The square bracket allows you to then select a row within this column based on some sort of condition. Condition being true, actually, specifically. So AB_freak, to select the data frame again, because we're using base R, and then $, to select the variable you want, in this case frequency, so freak. And we want to select the city where the frequency is the max value. So now in the conditional statement that we want to be true, we're looking in the frequency column, and we want the frequency that is equal to, make sure you have 2 equal signs here, where the frequency is the max of this frequency column. So this is saying basically it'll select New York City because it's looking in this column, this variable, and it's selecting the row, or it's selecting the city where the frequency is equal to the max value. And in this case, the max value of frequency is 45,756, which corresponds to New York City. So that's what this line of inline code is actually doing. So actually, when we knit this to an HTML, it might take a while because it has to run a lot of code. There's a lot more code after this as well. Okay, so this is actually a good example. So I went to knit this RMD file to HTML, and it didn't work, and it's throwing me an error. It shows a little X, and then it says line 306. So it's telling you, go to line 306. So if we scroll down, so 306, okay. What is it saying? Line 306, error in 1/6 times 1/6 times opportunities. And it's saying non-numeric argument to binary operator calls. Okay, what does that mean? Oh, okay, so yeah, we'll talk about this later on, but I was using this function as an example of what will happen if you put in an invalid choice. So this line of code isn't actually, it's throwing an error. It was on purpose in this case. So I'm just going to comment this out, and when we scroll back up to the top and rerun this code, it should work now. So knit to HTML, wait for it to run all of the code, And there we go. It actually knitted this time. Okay, so if we scroll down, we can see here that the city with the most Airbnbs is New York City. And it selected correctly the city with the maximum number of Airbnbs. And this is also bolded as we want. I'm going to just go ahead and close this now. So to move on, now we want to create a bar chart or histogram of the frequency of Airbnbs per city. So in order to do that, we're going to use the ggplot function. And the first thing we have to do is input the data or the data frame that we want to use. So in this case, AB freak. And this will be this data frame here. Then we put a comma and then AES, which is short for aesthetic. And in here, we'll put the X and Y value. So along the X axis, so this X axis, it's going to list each city. And then on the Y axis, it's going to show the frequency or the number of Airbnbs for that city. Then after that, you'll add a plus sign. On a new line, you'll add geom_call, which is the ggplot's method of adding a column or bar graph. And then you add another plus sign, and you'll use the function called labs to create X and Y axis labels. So on the X axis, we want it to be set equal to city. And on the Y-axis, we want it to be equal to number of Airbnbs. Also note that these are in double quotes because we want it to be read as a text value. So when we run this, it'll simply create that graph that was already being shown. So to create a pie chart, it's a little bit more involved. But it is very similar. So the first thing we want to do is call the ggplot function. And again, the first argument is your data frame that you're going to be using. So again, we're going to use the AB_freak. In the aesthetic or AES function or argument, we're going to set the X value to equal nothing. So we're going to have double quotes here, but it's actually just going to have nothing inside of it. The Y axis or the Y data is going to be %. And that coincides with this column or this column down here. So it's going to take that column. And the fill is going to be the city value. And this line of code here is telling our, okay, the city variable is not something that can be ranked necessarily, but it's a factor and factors can be ranked. So it's taking the text and assigning these sort of imaginary ranks to the data. Whereas if you had numeric data, it's already rankable just by the number itself. So if you had the values of 1 through 5, they're already rankable. The 1 value is a 1, the 2 value is a 2, etc. So you can easily order that data. Whereas categorical data, such as in this case a city, you're just telling our, okay, Broward County will be rank 1, Hawaii will be rank 2, Los Angeles will be rank 3. And in that way, it can then rank the cities as needed. It's not always necessary to use this, but you pretty much can't go wrong with just using the as.factor function for categorical data. So after you write that line of code, you'll add a geom underscore bar. So this is typically would create a bar graph, but with the next line of code, we will be creating a pie chart. So in here, we're just going to have a width of 1 and a stat is equal to identity. You don't really need to know what that is. You can look it up on your own if you want. Then add in the chord underscore polar function. And this is what takes that bar graph that we created in the last line and creates a circular pie chart. So the first argument is going to be set to y, and the start is going to be set to 0. That's 0 degrees. Again, you don't really need to know what this means other than you can copy and paste it and use it in your code. Then the next thing we're going to do is add a argument or function called scale underscore fill underscore manual. And what this lets you do is set your own custom colors. So the values is equal to C bracket, and then here are a list of hex values. And each of these hex values, so a hex value is the hashtag, and then 6 letters and or numbers that correspond to a specific color. So there are 1, 2, 3, 4, 5 cities, and there are 1, 2, 3, 4, 5 hex codes that correspond to each of those cities. And we want to, this is essentially creating, it's not only color coding the cities, but it's also acting as the legend. So the title of our legend will be the city. And that can be seen here as well, down here in the pie chart. This comment here is a website where you can go on and there are user-generated palettes of colors. If you're not really good at picking colors, you can go onto this website and there are plenty of color palettes or a series of colors that go together, and you can use those in your charts. So it'll give you what the colors look like, and then it'll give you the hex codes for each, and you can just kind of put them in place of these hex codes that I have here. And I encourage you to do so. Make it fun, make it interesting, or make it look like you want it to look. The next thing is you'll add a theme, and again, you don't really need to know what this is. Just add it in to your code. And then the last thing you're going to add in is the labs argument or labs function. And again, this just lets you add a title to the pie chart. So in this case, the title is % of Airbnbs, and this is the title here. And because it's a pie chart, it doesn't have an X and Y axis, so there's no label. And the 2 quotes with nothing inside just tells the X and Y axis aren't going to have any sort of label. So if we run this, you'll see the outcome. And just to show you, these hex codes do actually change the color. So if we put, instead of that, we put 1, 2, 3, 4, 5, 6 and run that, you can now see this is white instead of the color that it was. So I'm going to go ahead and put it back to what it was. Another good thing to note is that instead of just outputting the pie chart just straight up, you could create a variable called pie chart and run that. and it won't output, but if you then put pi_chart, you can run that and it'll create the pie chart. And this can be useful if you wanted to create a number of pie charts and you wanted to always start with this chunk of code. You could then add pie chart plus this, and let's go ahead and delete that. So if we rerun this, so pie chart is equal to ggplot plus geobar plus chord polar, and now we have pie chart plus scale plus theme plus labs. So if we run that and then we run that, you can now see it creates the same thing. So this variable now represents this line of code, or these lines of code. So that can be very helpful in certain circumstances. Next thing I want to show you is a way to represent categorical data with a word cloud. So some of you may have already seen a word cloud or know what a word cloud is, but it essentially is a frequency table or a bar graph or a pie chart, but instead of having a bar or a piece of pie represent the number, it just shows the word itself as a bigger or different colored word compared to the others. So it'll make more sense when you actually see it. So the first thing I want to do is remove duplicate tweets. So I'm going to create a new data frame called tweet_words. I'm going to input the tweets data frame and pipe it into the select function. And with the select function, I want to select only the tweet date and the tweet itself. So those are the only two columns I want from that. Then I'm going to pipe it into what is known as a distinct function. And this will look at both the tweet_date and the tweet variables. And it'll eliminate any row where the tweet date or the tweet is a duplicate of some other row in the data frame. I'm going to run that. We created our new data frame. Then what I want to do is create a list of all of the individual words. So again, you don't really need to know this, but if you're interested, it will create a word list. So I'm going to go ahead and run that. And you can see there are 355,267 words that were created out of this this code. So it's essentially just going into the tweets data frame and looking specifically in the tweet variable or the tweet column. And anytime there's a space, it's going to extract that word or those words in between the spaces and give them or separate all of the words essentially. And you're creating a list of words, which is exactly what it sounds like. You're creating a word, comma, space, word, comma, space, word. Just like you would create a grocery list when you go grocery shopping. So once we've created that, what I want to do then is remove symbols from the words. So in here, you can see right here, this line, there's a /anyone. And there are other times when, yes, see here, there's again in all caps and an exclamation mark. We want to remove those types of symbols so it's only the word itself. Because again, with an exclamation mark isn't going to match with the word again if it's on its own. So we have to remove the exclamation mark from that. And we can do that using the package called Stringer, which is in the tidyverse, and it has a bunch of functions that can be used to manipulate text or characters. So we're going to use string underscore remove underscore all. And then this, if you look in the cheat sheet that I uploaded on the Discord server of the Stringer package, you can see that these correspond to specific things that you want to identify in your text. So this one specifically will look for numeric digits in your text, and this function will remove those things from your text. So this is essentially going to look through the list of words that we created in the last chunk of code, or the last block of code, which is this. And it's going to go through and look for these different things. And you can look up what //w does, or //s does, or the digit or the space. And you can see what it's doing. So it's just looking on the right side, looking through this list of words and eliminating these things. So I'm just going to go ahead and do Control Enter to run that. And then the other thing important for a word cloud specifically is you really want to eliminate common words that we use in this case, the English language. If you're using French, German, whatever, Mandarin, you would want to eliminate common words from your word cloud. So for English, things like the, a, I, that, like things, words that are very commonly used that have no inherent meaning on their own. So I'm going to create this. This is a list. I didn't type this out. These are common words that I got off the internet that are already in a list form. And I created this variable called common, which are associated with all of these different words. Then I'm going to create another variable called word underscore list. And this is specific to the package I'm using to create the word cloud. So this function is associated basically with these words. So delete.stop.words, it essentially just means anytime it comes across these words, it's not going to add them to the word cloud. So I'm going to create that variable. Now we want to create a data frame, in this case called tweet underscore cloud. We're going to input the word list that we just created, and we're going to pipe this into a function called as.data.frame. This creates a data frame based on this word list, and this just lets us use the data in the way that we want. We're going to then pipe that data frame into what's known as the rename function, and this just lets us rename the column that was created. The name of the column was just a period, and we want to name it something more descriptive. So in this case, we want to rename that column as words. So words is equal to the period. So if we run just the as data frame function, so tweet cloud, and we look at it, you can see the header. So the column name is just a period, and that's not going to be ideal for when we want to call it in the future, which is why we use the rename function to create a new column called words, which is just set to the period. So if we run that and look at it again, you can see the column name is now words. And then what we want to do is lastly is pipe this into the filter function and eliminate using the exclamation mark where words is equal to nothing. So if there's any row where there is no word at all, then we want to eliminate that row. So let's go ahead and run all of that. Next thing we want to do is go through all of these words, and anytime there is a capital letter, we want to switch it from capitals down to lowercase. And this is because R is case sensitive. So if you have, say this word is can, but it's capitalized, and you have can, which is all lowercase, those two words are considered to be different by R. So we can use this function called toLower to take all of the words in that column, and if there's any capital letters, it'll switch them to lowercase. Let's go ahead and do that. Now if we look again, you can see the first one was can with a capital letter. Now it's can with lowercase. Also the CDC is all lowercase. And the last thing we want to do is count the number of words that are similar. So we're going to group by the words column. So anytime there's a word that's the same as some other word in the column, we're going to summarize it and create a new column called word_count and use the n function to count the number of times that word has come up by the word. So let's go ahead and run that code. And I renamed the data frame tweet_cloud2. So let's look at tweet_cloud2. You can now see that the word A has come up 525 times, or ABC has come up 129 times. So now if we create the actual data or word cloud, the function is called wordcloud2, and all we need to do is put in the data. So data is equal to tweetcloud2, which is the data frame we just created. And when you run it, it'll start going through and creating the word cloud. So the bigger the word is, the more prominent it is in the word cloud, the more times it's been said. So this word cloud tells us that Donald Trump, during his time of tweeting, he really liked to use the word fake, probably because he was saying fake news. He used to say fake news a lot. He also attacked the Democrats a lot because he was Republican, and he would say Democrats a lot. So he said Democrats in this case 1,177 times. He used fake 2,321 times. And one thing I did notice about this word cloud function is that we clearly listed I as a word to eliminate from the word cloud, but as you can see, I is listed very prominently in this word cloud. So function doesn't work super well, but it works well enough, and there's probably other packages that do the same thing that are maybe better, but this is the one I found. And it's not important, so I didn't really care. Okay, so now we're going to look at quantitative data. So the first thing we're going to look at is a histogram. And we're going to create a new data frame called AB_hist. And we're going to input the AB data frame and pipe it into the filter function. With the filter function, we want to select rows based on two different conditions. So the first one that has to be true is minimum nights. So the minimum number of nights that you have to buy the Airbnb is set to 1. So we don't want Airbnbs where you have to purchase at least 2 nights or at least 3 nights, etc. The other thing we want true is so both of these conditions have to be true at the same time. We want the price to be less than $500 per night. So we don't want to be buying an Airbnb that's too expensive. So if we run this, created the new data frame AB_hist. The next thing we can do is create the histogram. So we'll use the ggplot function. We'll input the data frame that we just created, and then we'll put AES, which is the aesthetic. We'll put price. Since we only need one variable to create a histogram, we're going to input price. Then a plus sign and geom_histogram. So it's its own function solely to create histograms. The bin width is 50. The bin width in this case represents the number of dollars that you want to show in each bar. So in this case, $50, there's going to be, so $0 to $50 for one bar, $51 to $100 for the second bar, and so on. Then we're going to add the labs function to create text-based titles for the X and Y axis. So the X axis will be that, and the Y axis will be that. And then the last thing we want to do is add in a scale X continuous function. And I'm going to actually run the code and then I'll explain that. So what this does is it changes the x-axis kind of grid lines. So in the background you can see that there are more x-axis lines, so the lines going up and down, there's more of them than the y-axis lines, grid lines, so the ones going left and right. And I just thought it was easier to read the information if it was coinciding with the bin width. So bin width is 50, and I'm saying I want you to create a x-axis grid line every $50. So it's going to start at 0, and it's going to go up to $500, and it's going to create a grid line every $50. So 0, 50, 100, 150, and so on. So that's how you do that. Now we're going to do an ogive chart, and because we're using dates for this, I need to use a library called, or a package called Lubridate, which lets you work with dates. So we're going to run that to load the library. First thing we're going to do is create a data frame for the tweets per month leading up to the ban. So ban date is the maximum tweet date. So the date in the data frame that is most recent, which is the day that he was actually banned from Twitter. So I'm going to run that. You can see over here in the environment, ban_date is associated with January 6th, 2021, and the time is UTC. Next thing we want to do is create a date for the election, the 2020 election in the US, just for more information on the graph. So we're going to do unique, because we only want one tweet date. We only want one row or data cell, rather, that's associated with this date. Since he probably tweeted multiple times on this date. We just want the one date. So we're going to look into the tweets data frame. We're going to look into the column tweet underscore date. And with the square brackets, this condition is to look in that column and select a specific cell. So in the tweets data frame and in the tweet underscore date column, we want to select the data cell equal to November 3rd, 2020. And this, as I said, this line of code that's highlighted here may select multiple rows. So this unique function is going to only select one of those dates because it's only going to be selecting 2020 11/03 multiple times. So we just want one of those since they're all the same date. So we use unique. So I'm going to run that code. I'm going to run this next chunk of code, or this next block of code rather. So tweet underscore ogive, we're going to input the tweets data frame, pipe it into the filter function, and we have this is kind of what I was talking about with the Lubridate library. This is why we needed the Lubridate data frame. So this is tweet date is greater than or equal to the band date, and we want it to output the months basically. You don't need to know this line of code. It's outside the kind of scope of the course. It's more advanced, so don't really worry about this. We're gonna pipe this data frame then into the select function. We only want the ID, the tweet underscore date, tweet, and car count columns. We're going to pipe this into the distinct function. And we want only tweets that are unique, since in the last kind of tutorial I talked about how this data set has duplicate tweets. And we're going to keep all of the data, so all of the variables, we're going to keep everything. And we're going to pipe that into a group by function. And I want to group by not only the month, but also the year. And then we are going to pipe that into a summarize function. And we're going to have tweet underscore date set equal to the last tweet date. And the frequency is set to the end function, which will count the number of tweets per month and year. So for each month and year combination, it'll count the number of tweets. Then from there, we're going to pipe this again into the arrange function, and we're going to arrange it by tweet date. And because I didn't specify, it's going to default to ascending order. So it's going to list the most historic tweet first, and then the most recent tweet last, which is what we want. We'll pipe that into the mutate function. We'll create relative underscore frequency and the percent column, which I already went over. We'll pipe this into an ungroup function. So what ungroup is doing is, because we use the group underscore by function to group the data frame, so it went from like kind of big and then we grouped it and the data frame got small again. The ungroup function takes that data frame where all the data is grouped and extends it back out to its ungrouped format. Then we'll take that and one last time pipe it into the mutate function, and we'll create a cumulative relative frequency by setting it equal to cumsum, which is the cumulative sum of the percentages. We run all of this code. And I encourage you to go through line by line to see what's going on, and it'll give you a better idea of what I'm explaining as we go down line by line. So we have this tweet ogive data frame. Let's look at it now. So we have the month, and then we have the year. And the reason I was talking about how it's important to kind of group by the month and the year at the same time is because these months, since the timeline is more than a year, so 13 months, we have a duplicate of the first month. So January is duplicated. So if we group by the month and the year, then this January 2020 is different from January 2021. And then we have the tweet date. So the last day of each month is the tweet date. So that's why we used the last function. The last tweet date was selecting the day of the month, the last day of the month that he tweeted. And then it's just a frequency distribution table, as we talked about. But the cumulative relative frequency is taking the percent. So the first cumulative relative frequency is the same as the percent column. But then when you move to the next month, it's taking the first row of the percent column, and it's adding the second row of the percent column. And then the 13 plus the 7 is equal to the 20. And then the 20 plus the 6.7 is 26.5, and so on, all the way up to 100. So it's your cumulative relative frequency will always result in 100% at the end, or at the bottom of your frequency distribution. So the next thing we're going to do is, just ran that just to show you that the cumulative sum ends in 100% at the end. So now what we can do is take this chart here, and we can create the actual ogive chart that was shown in the lecture slides. So we'll start with ggplot, like always. We'll input the data frame, which is tweet_ogive. The aesthetic will be x is equal to the tweet date. So along the bottom of the chart, we'll have the time, the month, and the year. And then along the y, we'll have the cumulative relative frequency. So this last column. And we'll add in the geom_line function, and add in the geom_point function, which they both do exactly what you think. This one adds the line to the graph. This one adds the points to the graph. Then we'll add in labels using the labs function. So the x-axis is the month, and the y-axis is the cumulative percent of total tweets in 2020 and slightly into 2021. Then we're going to add in, so with plus sign, add in scale_x_date. So this is basically saying the x-axis is months and specifically dates. So dates are read differently than text, which is important. So the date breaks that we want to use are 1 month, and the date labels is shown as this. You can look this up in Lubridate to see what these symbols mean, but you'll see when I actually run the code to create the graph. Then we're going to add in 2 geom_v lines, which will indicate the first one being election, the day of the election, so the Republican and Democrat US election of 2020. And we'll color that red. The other geom line will be the day in which Trump was banned, and that one will be light blue. So I'm going to go ahead and run all of this code. You can see it output same as your slide. So as I explained in the lecture, this somewhat like this very sort of linear line indicates that he pretty much was consistent in his tweets per month. Along the bottom, you can see the formatting. So what the %B and the %Y actually do is you have the month, 3 letters of the month, and then apostrophe, and then the last 2 digits of the year. And then the month label, cumulative % of total tweets in 2020 on the y-axis, and the percentage on the y-axis as well. The red line indicates the US election, which if you look closely, in September of 2020, he started increasing the number of tweets that he was making per month. And that makes sense because the 2 months leading up to the election, he started tweeting more actively during those months. And then after the US election, so December 20th and January of 2021, he sort of started to taper off with his tweets. And that again makes sense because he wasn't elected. So he didn't taper off that much. And as you may or may not know, Trump was tweeting about how the election was rigged, blah, blah, blah. And then this is just the hard stop of when he was banned from Twitter. So that's how you make an ogive chart. It's a little bit more complicated, but it still is an interesting way of representing data. So the next thing we'll do is the stem and leaf plot. So what we're going to do first is create a new data frame called AB_L500. The L500 is just to represent less than 500. So we're going to input the AB data frame, pipe it into the filter function. We're going to have 2 conditions to be true. So we're going to use the and symbol. Thus, both of these conditions have to be true at the same time. So minimum nights is equal to 1. So we don't want any Airbnbs that aren't available for purchase with only 1 night. So if you are required to rent the Airbnb for 2 or more nights, we don't want those Airbnbs. We also want the price to be equal to or less than $500. So we're gonna run that. And to create a stem and leaf plot, it's actually quite easy. You just use the stem function. You input the data frame and you select the variable you want to look at, which in this case is price. So let's run that. You can see the result of that function, if you're looking closely, is not actually helpful whatsoever. You have these values on the left, and what do they even mean? And if you're looking on the right side, you can see there's a plus sign and then there's a bunch of numbers. So this is actually very unhelpful and potentially misleading. So how do we fix that? Well, the thing is with this amount of data, so if we looked at n row and then this data set, so n row will count the number of rows. There's 57,358 Airbnbs in this data set. So that's one of the limitations of a stem and leaf plot, is you can't expect a stem and leaf plot to display a lot of data at once. It's kind of limited to a small amount of data. So let's pare this data frame down and only look at a very small subset of it. So again, we'll create a new data frame, input the AB data frame, pipe it into the filter function, and in this case we'll have 1, 2, 3, 4 different conditions, and because we're using the and sign, all of these conditions have to be true at the same time. So minimum nights is equal to 1, as it was in the last one. The price has to be greater than or equal to $200. So maybe you're looking for a nicer place. But the price also has to be lower than $250. So basically the price has to be in between $200 and $250. And you want to look at only Los Angeles. So if we run that code, we've now created a new data frame with those conditions. Now if we use the stem function, you can now actually see all of the data because there's only, let's see, nrow, and copy that, paste it into the nrow function. You only have 283 Airbnbs this time. So you can actually see all of the data. So let's look at it again. Okay, so basically there's, in the stem function, there are no arguments known as the scale and the width. And these are very important because they manipulate the way the stem and leaf plot actually look. The scale will basically, it's not an exact value, but basically your default stem and leaf plot, the scale will be equal to 1. And if you want to manipulate the height, so how many rows of data are showing, you will manipulate the scale. So if you put the scale to 0.5, it'll condense the stem and leaf plot to half its default size. And the width, as you imagine, tells the stem and leaf plot how wide it should be. So if we go ahead and run this code, you can see it's much vertically, it's compressed, and width-wise, it's showing more information. So that's also a very good point, is the scale and width you should always manipulate just in case, because in the first stem and leaf plot, it looks like it's showing all of the data, and you don't know that it's not. When you actually put in a width that's much higher, you can actually see that it's cutting off a bunch of data. So all of these values here are being cut off from the first one because the width of the first one isn't big enough. And here you can see it's a little bit easier to read because each line represents, this one is the 200s, this is the 210s, this is the 220s, 230s, all the way up to the 250s. This is easier to read than the 200s, but only up to 204. The 200s, but from 205 to 209, and so on. It's a little bit more confusing to read, whereas this one is more intuitive. So you can see from this, as I explained in the lecture slides, is that this first two numbers are the first two digits in the price value. So this is $200. This one is each of these individual numbers are the price of one individual Airbnb. So for instance, here there's 2 Airbnbs that cost $204. There's one Airbnb that costs $203. Or here there is one Airbnb that's worth $241. So this is an interesting way, and in some cases a very helpful way of displaying your data, but it does have its limitations. Okay, so the next thing I want to talk about is scatter plots. So scatter plots are very common, and there's something we will talk about more in the future when we go through regression. But for this segment, I'm going to use a data set acquired from Goodreads. So Goodreads is a website dedicated to books, reading books, reviewing books, etc., etc. And in this case, I'm going to show you a different method of creating a ggplot. So in this case, instead of just creating a data frame and creating a new data frame and then creating a ggplot with that data frame, what we're going to do is just kind of streamline that process. So we're going to take the books using the read_cv books.csv and to read it in. I'm going to just run all of this code so it's done. Basically, this is taking the books data frame, piping it into the filter function. And we want two different conditions to be set as true. First of all, we only want books that are equal to or greater than 200 pages. We don't want short stories or anything shorter than a novel. We also want, so using the and, we also want text reviews count to be greater than or equal to 0. So text reviews count is the number of people that have reviewed the book but also given it some sort of text-based review. So they wrote down comments about how they felt about the book. So we only want books that have actually received a text-based review. So one or more. And I should mention, what we're trying to do with the scatter plot is understand this statement. So are people more willing to write a review for a book that was rated well? So a book that they thought was good, are they willing or more willing to write a good review? In this case, our null hypothesis would be just that no, the book's rating has nothing to do with the willingness of a person to write a text review. But the alternate hypothesis is sort of the hypothesis that you think to be true, is that a book's rating will influence their willingness to write a text review. So if they thought the book was really good, they are more likely to write a review. So first thing we're going to do, pipe the books data frame into the filter function, make sure the number of pages is greater than or equal to 200, and the book also has to be associated with at least one or more text reviews. We're then going to, instead of setting that equal to a new data frame, pipe it straight into the ggplot function, so we can skip the data argument of ggplot because it already knows to use this data frame that you piped into it. And we can skip right over to the aesthetic function or argument, where x is equal to average rating, because this is the predictor variable or the independent variable, and y, so the y-axis is equal to the number of text-based reviews. So this is our dependent variable. It is my idea or assumption that the better a book is, the more text reviews it'll have. So I'm using average rating as a way or a means to predict the number of text reviews. To create a scatter plot, we are going to add geom_point function, and then this will create the points on the graph. And then we're going to add in a regression line. So we're going to use the geom_smooth. The method is equal to lm. This is the LM represents linear regression, and SE is equal to false. I don't really need to know that, but this line of code just adds in a regression line or a line of best fit. I'll talk about that later in the regression slides. I'm going to add in labels to the graph. So X is equal to average rating. Y is the number of text-based reviews. And then we're going to add in scale X continuous and scale Y continuous. This adds the grid lines as I discussed in that other chunk of code. So for the X-axis, it's going to start with 0 because the lowest average rating can be a 0, and an average rating can be at maximum a 5, so 5 stars out of 5 stars. And we want a grid line every 0.5. So that's how this is, how the grid works on the X-axis. On the Y-axis, it's going from 0 to 60,000 reviews, and it's going to create a grid line every 5,000. So that is how this is working. Again, you don't need to know this, but the regression line in this case, very weak. There's no real association between these two things. So that was interesting to me. I would have thought better books would have more reviews, but I was apparently wrong based on this. Next thing I want to show you is how to create a choropleth map. So these are the libraries that we need. These are the install packages. Again, highlight them, Control-Shift-C. You can then run that code if you need to. I've already installed them, so I'm going to re-comment them. We do, however, need to load in these libraries. So once we've done that, we can read in the data frame showing the cost of living in 2020. So we're going to do that. And then we want to rename this data frame, because if we open it, the cost data frame, we want to rename some of those columns. So this country column, instead of country, I'm going to rename it as name. And this is because we need to merge data, and we need the columns to be the same name in order to join them. So I'm going to go ahead and create that. Then we will create the countries using the ne_countries function, which is from, I think it's the Natural Earth package, not positive, I forget. And this basically just, it imports a shapefile of countries that we can use in R, which will be more apparent when we create the map. The reason I renamed the country column to just name is because in this data frame, the countries are called just name, which if you scroll into here, I mean, it's not that important, but just believe me that, here we go. There's this column is called name, and it's associated with the names of the countries. So that's why we did that. Now we want to join the cost information, so the cost of living, all of that information to the spatial country dataset. So we can use the merge tool. We're importing the countries, the spatial countries, to the cost information or dataset by the column called name. So it'll look in both tables, and it'll look for rows with the same country name, and it'll join them based on that. We can go ahead and do that. And it has created this data set that is also spatial. We can then create bins based on natural breaks. So this is a function, I think from BAM tools, but I'm not positive. Again, I mean, you can just look it up. Get Jenks breaks. This will create natural breaks using the cost of living index, and it'll create 6 groups. It's actually creating 5 numeric groups, and then it's creating 1 extra group that's just NA values. So those are our bins. That'll be important for the map that we create in the legend. This is creating the color palette. So PAL represents palette, short for palette. We use the color bin function, and we'll use what's known as the yellow to red color palette. That's what it is. It's just that text. The domain is equal to the cost of living index, and the bins are equal to the bins variable we created with the natural breaks. Go ahead and create that. This I'm not going to bother explaining. Basically, it's just HTML to format the leaflet map. And HTML is, if you don't know, another programming language. HTML is used for websites and stuff. So this is just used to format something in the map. You don't really need to know that, though. So this is a leaflet map. I'm going to actually run the code, and then I'll explain what stuff is. I'm going to run this. This created this map. So you can see you don't actually even have to click on the map. When you hover over the polygons, it'll come up with this pop-up that says the country name, it's bolded, and the cost of living index. So the higher the value, the more expensive it is to live there. So you can see North America has a very high cost of living, excluding Mexico. And Norway, Iceland, France, kind of most of Western Europe is very expensive, as well as Australia and Japan. And then the rest of the world is varying degrees, but mostly low cost of living. And again, you can zoom in so you can see more detail. The legend down in the right is created using the palette of colors, the yellow to red. And you can see here, 1 extra grouping is NA values. So if we look at the leaflet information, so I mean, I will just say this HTML code is used for the label, the pop-up labels. And you can look this up if you're interested. So to create the map, you first use the leaflet function. You input your data, which is the country_cost data frame that we created that has a spatial component. We pipe it into the add provider tiles function. We do providers, $, and it is my preference to use cardodb.darkmatter. You can select whatever base map you want that you think is interesting. Then we can pipe this into the add polygons function. So you can see here, for formatting reasons, the polygon function has a lot of information in it. All of this code right here is encapsulated in the add polygons function. But because it's so much information, I wanted to create spaces between the chunks of, or the blocks of code, so you would understand more easily what's going on. So the first thing we do is use the fill color argument. This adds the color based on the cost of living index value. So you do a little squiggly tilde, I think these are called, PAL, which is the palette that we're using, and the cost of living is the numeric value that will give it color. There's a comma here, don't forget that. The next argument is, so this code here changes the way the colors look as well as the borders of the colors look. So the weight is 1, opacity, color is black, dash array is 3. So this is like, instead of a solid line, it's a dashed line. And the opacity of the fill is 0.7. So it's somewhat transparent. You can see, like here in France, you can see the word France behind the block of color. And the next block of code is to create the hover effect. So when you're highlighting, or when you hover over a country, you can see it goes from being a dashed black line to a solid gray line. It sort of seems to pop out at you. So this is the chunk of, or the block of code doing that. So there's a highlight argument, and then these are highlight options. Not going to really explain this, but these are the options that I set. Bring to front is true. That means it kind of pops out at you. And then the label is set to labels. The next block of code will add a label on the mouse hover. So when you hover over a country, it comes up with this pop-up. So this is, I'm not going to go through this. This is just kind of basically HTML code. And then lastly, we're going to pipe this. So all of this was all just that add polygons function. And you can see here, there is this bracket corresponds to this. So when you have the cursor to the right of the bracket, you can see it'll highlight the corresponding bracket. So we're going to pipe that then into the add legend function, where the palette is equal to pal. Values are the cost of living index. Opacity is 0.7, and there's no title. And the position on the map is bottom right. So it's always going to be in this bottom right location. You can see, if you look closely, you can actually see through the legend. The next thing we're going to go through is probability, and we're going to just use that same Catan example that I used in the slides. But I'm going to show you how to do it easily. So we're going to create a function called dice_roll using the function. We're going to create a function called dice_roll. The one argument is the outcome. So the outcome is when you roll the dice, if it comes up with snake eyes, the outcome is 2. So this function is going to have a series of if else statements, and it's going to then have the math in order to calculate probability, and then it's going to return the probability with a %. So in the function, you have the first thing that we want to calculate is opportunities. So say you input as your outcome. I'm gonna run this first, and then I think it'll make more sense. So the function has been created. We scroll down here, dice_roll is a function, and the argument it takes is outcome. So at the bottom here, we have dice_roll, and then in brackets, we have an 8. And if we run this, it'll tell you the chance of, or the probability of rolling a 8 on 2d6 is 13.89%. So the way that's being calculated is through this code here. So these if-else functions are used to tell R how many opportunities are there to roll each value. So the first thing is we're creating a variable called opportunities, and we want to set opportunities to set to a numeric value based on the outcome roll that we're trying to roll. So the first thing is write if, and then in brackets, this is the condition. So if the outcome is equal to 2, we want to set opportunities equal to 1. And this first if statement has the condition, and then it has a squiggly bracket, has the 1, which opportunities will be set to, and it has a squiggly line. So what if the outcome you input is not 2? And what if it's 3? Then you write else if, and then in brackets, outcome equal to 3, set opportunities equal to 2. And it's in these little squiggly brackets. So if you write dice_roll and you put the value of 3, so you want the probability of rolling a 3, it'll set opportunities equal to 2, because to roll a 3 on a die, or on 2d6, die A could be a 1 and die B could be a 2, or die A could be a 2 and die B could be 1. If you want the outcome to be a 4, then you just do else if the condition is outcome is equal to 4, so you're rolling a 4. There are 3 opportunities to roll a 4. There are 3 combinations of the 2d6 that will return a 4. And you can continue doing that all the way up to outcome is equal to 12. And you can see on each of these times, the opportunities will be set. Opportunities will be set equal to a 1 if the outcome is 2, a 2 if the outcome is 3, a 3 if the outcome is 4, and so on down the line. And at the very end, we want to have a statement be printed out if you put in an outcome that's not possible. So if you put in an outcome of 1 or 13 or -5, it will print a sentence that says not a valid choice, because when you're rolling 2d6, the outcome can only be a 2 up to a 12. Any other number is not possible. So what's happening in the function is when you put in dice_roll and put an 8 in there, the first thing it's going to do is it'll read this line of code. It'll say, if outcome is equal to 2, well, that returns a false because the outcome here was set to 8. So it's reading this and it's saying 8 is equal to 2. That's false. It'll return false. So it then goes, well, okay, that's false. What's the next line of code say? If the outcome is equal to 3, well, outcome equals 8, so 8 does not equal 3. Thus, this is also false. Then it goes to the next line. Well, does 8 equal 4? No, it doesn't. That's false. So it'll keep going through each of these lines of code in order until it reaches this line of code. And this line of code will be outcome is equal to 8. Outcome is 8 in this case, so 8 is equal to 8. That returns true. So now R will be like, okay, well, this statement or this condition is true. Thus, we'll set opportunities equal to the value of 5, because to roll a 5, or to roll an 8 rather, there are 5 different combinations of 2d6 that will result in an 8. So that's how this first if else, or if else if and else statement works. So in the same regard, if you put in dice underscore roll equals -1, it would read all of these lines of code, all of these conditions, and -1 will never equal, -1 doesn't equal 2, 3, 4, 5, 6, all the way up to 12. So it'll then skip all of these lines of code, and it'll come to this last else catch-all line of code. And it'll be like, well, I mean, none of the conditions are true, so we will print off to the console a text that says not a valid choice. So once it's done going through these lines of code, hopefully you have input a valid choice for the outcome. So let's say, going along with this example of 8, it has come to here, and this is a true statement because 8 is equal to 8. So opportunities is equal to 5. It'll come down to this next line of code, which is probability is equal, or will be set equal to 1/6 multiplied by 1/6 multiplied by opportunities. And opportunities is this same variable. So because you input an 8, it reads this as true, and then it sets opportunities equal to 5. So in this calculation here, it'll take 1/6 times 1/6 times 5, because to roll an 8, there's 5 combinations. And it'll multiply that outcome by 100 to create a % outcome. Then it's going to go to this next line of code. It's going to overwrite the probability value, and it's just going to round using the round function. It's going to take the probability you got and round it to 2 decimal places. And then the last function we use is return, which will return it'll use the paste function to add together the numeric probability that we just got from here, and it'll add a % to the end, and it'll return it to the console. So when you run this dice underscore roll 8, it's reading through here, stops here because this is true, sets opportunities to 5, then it goes through this line of code where this value is equal to the 5, and then it's overriding that probability by rounding the probability to 2 decimal places, and it's returning a probability plus a %. So here. So the probability of rolling an 8 is 13.89%. We could change this to a 2, and the probability is 2.78%. So as I was saying earlier, if we have dice roll 1, it says, well, that's not a valid choice. It still tries to do these lines of code, but and that's why it's throwing an error like here. There's almost certainly a way of skipping over that line of code. I don't know how to do it in R. I know how to do it in Python, not R though. So I'm going to just comment that out. The next thing I'm going to talk about is the probability distribution. So we are going to go back to using the books dataset or data frame, we're going to create a new data frame called books underscore PD, which is probability distribution. And we're going to try and answer the question, what's the probability of a book having an average rating above 4.2 out of 5? So we're going to create this data frame, input the books data frame, pipe it into the filter function. We're going to eliminate the NA values from NA values from average rating, eliminating using the exclamation point. So if is.na, so if there's an NA value in average rating, the is.na function will return a value of true. So if true is equal to true, we want to eliminate that row. We're going to then pipe that data frame into the summarize function. And we're going to create 3 different variables. First one is z-score. Set that equal to this formula. This is just straight from the slides, so I'm not going to go over it. We're going to create a z%. This takes the z-score and converts it to a percent, and then the pnorm function, and then we're going to have the probability of the outcome. So again, this is just from the lecture slides, and I'm going to go ahead and run that. We can look at the outcome. So right here. So this is what is outputted as the z-score, the z%, and the probability of the outcome. So in this data frame, there's the z-score, z%, and probability out. If you wanted to get the probability of that outcome from there to inline code, this is how you would do it. So you'd use books PD, looking at that data frame, and then you just want to select the probability underscore out value, and because there's only one row in this data frame, it's just going to select this one value. So this is, you don't actually need to do this individually. It's just to show each individual formula on its own. But what if we wanted to do this, but we wanted to use a different threshold, average rating threshold each time? It would be really annoying to copy and paste this code a bunch of times and change this one value each time. So what we can do is create a function. So we're literally just taking this data or this code block and putting it into a function. The biggest thing is we're going to have 3 different arguments this time. So the function is going to be called probability of exceedance. It's going to be set equal to using the function function. And the 3 arguments are going to be the threshold, so the average rating that you want to see with the probability of exceeding, the data frame that you want to input, and the data frame column name, so average rating in this case. So these are the 3 arguments that you'll need to input. So let me run this again, and I'll show you the outcome before I go through the code. So once this is run, we now have this probability of exceedance function, which takes threshold, data frame column name. Now we have here, so let's say, what's the probability of a book exceeding an average rating of 3.5? So this is a little easier now because we don't have to write out all of that code. We can just write this one line of code. So probability of exceedance, first argument is 3.5. That's our threshold. Books is our data frame that we're looking in. And average rating, in quotes, is the column that we're looking at. So if we go ahead and run that, you now see, okay, well, the probability of exceeding a 3.5 rating is 89.49%. Now, to advance this even further and to really explain why functions are so powerful is, what if you wanted to look at the probability of a book exceeding an average rating of multiple different ratings all at once? So you don't even have to write out 10 lines of code to change the threshold each time. So for this purpose, we can use a for loop. To those of you that are really into coding, there are better ways of doing this than using a for loop, but I think it's the most intuitive way to do it. So a for loop will look through rows of data in a data frame. The I can be anything. This is just a variable name that you're then going to reference. But for whatever reason, I is almost always the default variable name in a for loop. So it's going to do for I in the sequence, so 1 to 5 by 0.5. It's going to start at 1, it's going to end at 5, and it's going to increment at 0.5. So it's going to go 1, 1.5, 2, 2.5, 3, and so on. And each time the for loop, basically every time the for loop iterates through the sequence, that's probably why it's I for iterate. So each time I is iterated through the sequence of numbers, it's going to run this line of code or run the block of code that's in these two squiggly brackets. So it's going to use the paste function to include probability of exceeding an average rating of space. I is the next argument in the paste, and I will start out as 1, and then I will be in the next iteration, it'll be 1.5. Next time it's iterated, it'll be 2, and then so on. The next thing is semicolon, a space, and then we're going to have the function that we created. So probability of exceedance. The first argument is I, and I will be 1, 1.5, 2, 2.5, etc. So this is our threshold of average rating. Books will be our data frame. Average rating will be our column that we're selecting. And then after that, the last argument of our paste will be just a %sign. So let's go ahead and run this. So now you can see the power of using a function with a for loop. So the probability of exceeding an average rating of 1 is 100%. Basically, all books exceed a 1. All books actually exceed up to a 2. The lowest rating is a 2, at least in this data set. Actually, no, it's a 2.5 rather. It's 2.5 is the lowest rating in this data set. And then you can see after, as you increment the average rating up by 0.5, the percent or the probability of a book exceeding that rating goes down. I'm not exactly sure why this isn't 0. I don't know, unexplained. It should be 0 because a book can't have a rating higher than 5. It's 5 out of 5 or it's nothing. So to go through the actual function itself, it's essentially the exact same as this data set. The major difference is just the variables or data frames or column names are called something else. So in the function we created, the 3 arguments are called threshold, df, and df underscore call underscore name. So in the first line of code here, we have df underscore pe, so data frame underscore probability of exceedance. This coincides to this. And the next one is df, so this coincides to this data frame. I actually would like to correct that this isn't necessarily it is the same data frame, but this isn't actually this, because you're creating a new data frame based on the book's data frame, so this could be anything. So your data frame, so books in this case, this is the placeholder for books, is then piped into a filter function, and this is the condition. So in this case, this is the condition. So let's kind of skip over the first part. This part of it is the exact same, and then this is placeholder for the average rating column. And this part of the code is necessary to tell R that this average rating is a column, and this tells R, okay, this df underscore call underscore name, this is supposed to be read as a column name. It's not just a line of text or a string of text, it's actually a column name. So when you're using a function and you're trying to call a column name, you have to use this exclamation point space SYM. So it'll read this instead of R reading it as a string, it'll read it as a column. So that's the only difference between this line of code and this line of code. Then the summarize function is, again, basically the exact same, except instead of using the mean, instead of using this 4.25, we're using the threshold, which would be this value here. And the mean, so up here, the mean of average rating, we again have to use that this function to call a column name. And again, over here, we have to use the same function to do that. And then the rest of it is the exact same in terms of the summarize. And then the last thing is to return this data frame that we created, and then $prob underscore out, which is this same column that we created in the summarize function. So once you've created that, you can see how this function actually works. So it's just changing the threshold. It's inputting the book's data frame, and it's telling R which column to actually use. And then in the for loop, instead of using the same threshold value every time, it's going to iterate through the values of 1 through 5 with increments of 0.5. And it outputs as a sentence in this case. So the power of a function, I think, was shown very well here, and I definitely encourage you to practice them. So the next thing I want to show you is how to geo-visualize the probability of exceedance on an actual map. So the first thing I'm going to do is run this line of code. This basically is a RStudio function that tells R don't use scientific notation and just show the numeric value with all of its decimal places. So that's what that does. We're going to import the rainfall CSV file, and then we're going to do a little data maintenance. First thing, so we're going to overwrite the rainfall data frame by inputting the rainfall data frame, piping it into the select function. We're going to select these columns, and you have to use the back quotes because there's spaces, and that's what we want to avoid. We're going to pipe that data frame into a filter function, and we're going to select the rows in the data frame that show this, because this data frame has a lot of different rainfall variables, so we want to eliminate them. I'll just show you what the rainfall data frame actually is showing. So you can see here for Afghanistan, say there are multiple stations where it's calculating rainfall, and then there's mean monthly value for that one. But say for Albania, there's mean monthly value, minimum monthly value, first quintile. There's a whole bunch of different ones. So we just want the mean monthly value. Then we're going to filter out where the computed value is equal to negative 9,999.9. This is a common thing in data sets where if the researcher that actually compiled the data set doesn't have a data value for that data cell, they'll input a numeric value that is often much, much higher or much, much lower than any other data value to indicate that that is missing information. So in this case, negative 9,999.9 indicates that the data value is missing. So we don't want those rows. So I'm going to go ahead and run all of that. Then we're going to create a annual rainfall data frame by inputting the rainfall data set that we just created, data frame, pipe it into the rename function. So we're just going to rename the country or territory column to name. Rain underscore millimeter will be set to this variable. Just easier to work with variables with no spaces. We're going to pipe that into the group by. We're going to group by the country or the name. We're going to then pipe that into the summarize function. We're going to create a bunch of different variables. First one is mean rainfall, so that is just the mean of rainfall. Standard deviation of rainfall, which is SD of rain millimeters. And then we can create the z-score, z%, and probability based on these two variables that we just created. And we'll pipe all of that information into the filter function, where we will look at mean rainfall is greater than or equal or greater than 10,000 millimeters, or so one of these two things can be true, and it'll select is.na the standard deviation. So if there's a NA value in the standard deviation of rainfall, and if there's an NA, we basically just want to eliminate the NAs. That's what that's doing. The double negative is confusing. And if you have to write a line of code like this, and you're confused by the double negative, you can just test it, see if it worked, and then if it didn't, then just do the other thing. So instead of false, you'd put true in that case. Then we'll pipe that into another filter, and this line of code will eliminate the brackets from the country titles. some countries have things that are in brackets, and we just want to eliminate the brackets. And then lastly, second last, we'll pipe this into a mutate function where the name is equal to this function. You don't really need to know how to do that. It basically just converts the capitals to lowercase and removes any text that are after a comma. And then lastly, pipe that into distinct. So we just want to keep rows where the country, we just want one row per country, but we want to keep all the variables. So let's run all that code. Then moving on, and we can just do a little bit more, and then we can actually map this data. So let's create a new data frame called country_rain, where we're merging countries to the annual rainfall data frames, and we're connecting them by the name variable. So countries will be joined to countries. Run that. We'll create the bins. Again, we're creating, we're actually not creating based on natural breaks. I shouldn't have put that. It's not natural breaks. We're just doing, I think equal interval, where you're just having 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 100. So those are the bins we're doing. And the bins represent the percent chance or the probability a country will exceed the threshold of rainfall. The next thing we're going to do is create a color palette for the legend. And in this case, we're going to use blues because blue is representative of rain. The domain will be the probability of exceedance, and the bins is equal to the bins that we just created. And then again, we're using HTML to create fancy, nice looking labels. And again, you can look this up if you're interested. This is the package HTML tools, if you want to look it up. And then to actually create the map, the first thing we do is use the leaflet function and then input our data, which is country_rain, which is the merged data that we just created. Add a provider tile. So providers, in this case, I'm using esri.world_shaded_relief as the bottom. I found this just made more sense in this context. Pipe that into an add polygons function to add the countries. And I'm not going to go all through this again because it's essentially the same as the other example. The one thing I wanted to point out, though, is you can add the grid lines of the longitude and latitude. And here is basically you can toggle this. So on the actual map that's output, you can toggle the lat and longitude lines on and off, which is cool. And this last line of code is the thing that actually lets you toggle it on and off. This is basically just the lat and longitude lines, and this is what makes it toggleable. So I'm gonna just go ahead and run all this code at once. And as you can see, it outputs this nice interactive map. Just like the other one, you can highlight it and it'll tell you information about that. So in Norway, the probability of rainfall exceeding 2,000 millimeters is 10.72%. The United States probably doesn't have data because I was too lazy to go through both country files and change all the countries to match, because not all countries are always listed as the same country. They might have other, for example, United States could be USA, or it could be United States, or it could be United States of America. So I didn't want to go through the countries and do that. It's not worth it. But yeah, you can kind of scroll in or zoom in rather, and you can see the relief. I thought that was interesting because the mountain ranges influence rainfall, so that would be interesting if you were actually studying this. And then you can see the percent that it will exceed the rainfall value. The other cool thing you can do, so the longitude and latitude lines are cool because rainfall is also dependent on the latitude lines. So I wanted to have them in there, but they can be a little distracting, so you can click them on and off, which is really cool. So yeah, that's how you do that, and that's a cool example of how you can use probability exceedance in a geographic way. And I know, again, this was probably very tedious for people that know R well or know a programming language, but for those of you who are just learning, I hope this was really helpful, and I hope you can kind of use these two tutorials to basically just copy and paste code from these tutorials into the assignment, and you're just modifying the data frame names or the variable or column names, and you can complete your assignments hopefully relatively easily. I know it's a lot of information to take in all at once, but I promise you in almost every case you can just copy and paste code and just modify it slightly. Anyways, I hope that helps. I hope that gives you a better understanding of the lecture slides. Thank you.